let me simplify this just a little bit before I multiply on the left by v. So I get 1 over I, and the first column is 2 minus I, minus 2 minus I. And then if I multiply the quantity 1 plus I over 2 and 2 minus I together, then I get 2 plus 2I minus I, which is I, and then so I get 3, let me not do this too fast, right? So we have 2 plus 2I minus I squared all over 2. And then downstairs I have, if I multiply these two terms together, I have minus the quantity 2 plus I minus 2I minus I squared all over 2. So I get 1 over I, 2 minus I. Now the i's cancel here, so I get 2 plus I. Then I squared is negative 1, so I get 3 plus I all over 2. Then minus 2 minus I minus the quantity 3 minus I all over 2. Okay, so this, in short, is D times V inverse. Now what I want to show is if I multiply this matrix by V, I should get A back. So assuming I didn't make any mistakes, V times D times V inverse will be this matrix times the matrix we just computed, okay, so let me bring the 1 over I out front, then row against column as usual. So I get, this is going to be messy. All right, so I get minus 1 minus I over 2, 2 minus I, minus 1 plus I over 2 times negative 2 minus I for the first entry. Then I get, for the second entry, minus 1 minus I over 2 times 3 plus I over 2 plus 1 plus I all over 2 times 3 minus I over 2. All right, and then the last row should be, or the second row should be easier, because then I have this row against this column, so minus 2 minus I plus minus 2 minus I is minus 2I. And then if I add, if I take 1, 1 against the last column, I simply add those together, the 3's cancel, and I'm just left with I. Okay, so I just have to simplify the first row. Okay, so if I put everything together, let's see, so I have 1 minus, so I have minus 1/2 times 2 minus I minus 2I plus I squared minus 1/2 negative 2 minus I minus 2I then minus I squared, and then I'm running out of space here. Okay, so what should I do? Minus 1/4 times 3 plus I minus 3, which is minus 2 I minus I squared plus 1/4 3 minus I, so 3 plus 2I minus I squared minus 2I I. Yuck.
This looks like one of those things that they show in movies to like make it look like you're doing it. Mathematics.
That's true. That's true. Okay, we're almost through. I just want to convince you that this procedure works. That we should get A back once we reconstitute everything. Okay, so I have 1 over I. And so, let's see, so I squared is -1, 2 and -1 is 1, 1, okay, you know what? I'll leave it to you as an exercise. I've already convinced you. Here's the thing, the last 2 entries, the 2 entries in the final row are right. So I believe this is correct. So I should get 3i here, and then I here, so I'll leave that to you to verify. And then we know for sure that the last row is -2i, I. So then after all the i's cancel, I get 3, 1, -2, 1, which is A. Okay, that's all I wanted to show you. So I'll leave the remainder of the algebra to you to work out, and we should get A back. Okay. All right, so that's all I want to say about the process of diagonalization. Now I want to go into why we care about diagonalization. Any questions before we move on? Yes?
Do we have to do those like problems on the exam?
No. I'll have to think about it. Okay. Yeah, I can't answer that right now. All right. I have to think about whether it's feasible in the time allotted.
Okay, just.
All right. Okay, so basically the procedure is find eigenvalues, find eigenvectors. Certainly something like that will appear on the test.
Okay.
Whether or not I'll ask you to put it all back together in the end to get A, I'm doubting it now, if this is any indication. All right, so then you find the eigenvalues, eigenvectors, then you can construct the matrices V and E and diagonalize this way. All right, so now what I want to do is I want to try to convince you that this was all worthwhile. So I'm going to move on now to section 5.7, which deals with systems of linear differential equations. Okay, so this is where it all sort of pays off. Okay, so differential equations, which I'll abbreviate this way. So differential equations describe any model or system which varies continuously with time. And we always represent time by lowercase t. Okay, so as examples, let's say a particle or an object moves in 3-dimensional space with position vector x of t. Okay, so you give me a time, t, I plug into x, and that will output a vector whose components give me the position of the object in 3-dimensional space. Okay, so it moves in 3-dimensional space, and it's subjected to some force. All right, so let's say that the total force acting on the particle is F. And now I'm going to assume that the force field is a function of x. So this is not an outrageous thing to do. You're actually sitting in various force fields that depend on position, namely gravity. Gravity changes as you move away from the gravitating mass, namely the Earth. Electromagnetic fields are all throughout this room. Those also exhibit forces which depend on position. Okay, so if you just had some position dependent force acting on a particle, then Newton actually tells us that the second derivative of the position vector as a function of time is 1 over the mass times the force evaluated at x. So essentially, this is an equation which tells us how x behaves as a function of time, and involves the derivative and the second derivative of x. So it's a differential equation. So it's a differential equation which allows us to predict the future of the object if we know its position and velocity at some time. Okay, so I don't expect you to know physics in this class. I'm just trying to motivate why we care about differential equations. So this is one very powerful motivation for studying differential equations. So in principle, if you have all of the forces that act on the system and a powerful enough computer, then you can predict the future of that system using this differential equation. Okay, so this is one example of the applications of differential equation. And then other examples, really there are just too many to go into in this class. That's why we have a separate class, 3F, for differential equations. So another example, for instance, comes from predator-prey systems. So one example that I always like to go over with my calculus class involves a basic model that involves, say, two competing species. So in the example that I go over in 3A, we call WT the population of Arctic tundra wolves.
That's right.
Yes.
What's right next to example? Product?
Oh, predator-prey.
Oh.
Predator, yeah. So we let capital WT be the population of Arctic tundra wolves, and C of T is the population of caribou. So a very basic model describing their interaction, because the tundra wolves eat the caribou, so the caribou is the prey, tundra wolves are the predators. A very basic model would describe the rate of change of their various populations. So let's say we're interested in the rate of change of the caribou population. If they were completely unchecked, they had all the vegetation they wanted, they would grow according to their population. So if their population was a certain size, they all eat and breed and they keep reproducing caribou. So then their population would explode exponentially, but the presence of their predator would bring that population back down, because then the more caribou there are, the easier they are to hunt. And so they'll get gobbled up by the tundra wolves.
Are those C's and W's actually C of T?
Yes. So I'm just suppressing the time variable. So they are functions of time, I just don't feel like writing time.
A and B are just constants.
Yeah, and they're just constants fixed by the model. Yeah. And then the tundra wolf population, if they had no food, since they don't hunt each other, they don't eat other tundra wolves, then their population would die off exponentially if they didn't have a food source. But if they have a food source, namely the caribou, then their population would go back up because they could eat the caribou. So there's a complex relationship between the populations of the two species as functions of time. And this would be a very basic predator-prey model where A, B, C, and D are positive constants fixed by the model.
Not to be confused with capital C, right?
Not to be confused with capital C. Yeah, capital C is for caribou. Yeah, little c is just a constant. So you may not care about the interaction of a predator-prey model, but these models are amazingly successful in other areas, like in economics, where you have a group of, or several groups competing for limited resources. Then predator-prey models are actually very accurate in describing behavior, the interaction of all those groups. So in economics and finance, biology, even to social sciences to a degree, predator-prey models and differential equations in general are very useful in modeling anything that evolves continuously with time. All right. So that's sort of my pitch for differential equations. Any questions? Okay, so yeah.
You said varies continuously with time. Does it have to be time, or can it be like another parameter that continuously changes? Or
That's a good question. So for right now, I'm focusing just on time because we're going to be interested in single variable functions. But if you have functions of more than one variable, then you're looking at partial differential equations, and those model of a different variety of physical and mathematical systems. So it doesn't have to be time. No, that's the short answer. But for us, I'm just keeping things simple and focusing only on time. Okay. All right. So solving differential equations is a very broad area of math, so much so that it gets its own class here, 3F. So I'm not going to be able to cover nearly a fraction of what's available on differential equations. But for us, given what we know, we're able now to solve linear systems of differential equations of first order. So I'll explain what that terminology is, or what that terminology means in just a moment. Okay, so solving linear systems of differential equations, we can do that with the tools that we have, and it turns out that the nonlinear systems that I described in the examples can be analyzed using linear systems near equilibrium points. So when I finish our discussion of linear differential equations, I'm going to come back to this predator-prey model and show you how linear systems can actually help us understand the behavior of this nonlinear model. So it's nonlinear because I'm multiplying C and W together here. And because I'm multiplying C and W together, this system is not linear. But I can show you that when the populations reach an equilibrium, so when the caribou reproduce at a rate that matches the consumption of the tundra wolves, then I can show you that if you nudge that system just a little, you can use linear systems to understand if those equilibrium points are stable or not, whether or not a little nudge in the population will send them cascading off to oblivion, or if everything just kind of balances out and just rebounds and maintains the equilibrium.
So is it you set the derivatives equal to each other at that point?
Well, the equilibrium point would be where the populations don't change at all. So you set both dc dt and dw dt equal to 0, and then you solve for their populations. So that's basically where I'm heading to conclude the section on differential equations, but we have a little bit of terrain to cover before we get there. All right, so that's sort of the motivation. So linear differential equations are very important. They model very basic phenomena that appears in a variety of situations. But more importantly, nonlinear systems model more interesting phenomena like predator-prey models, or in the case of Newton's second law, particles undergoing some kind of force field or experiencing a force field. So it turns out that those nonlinear systems can be analyzed near their equilibrium points using linear systems. So linear systems are very important to understand their nonlinear cousins. Okay, so that's sort of the motivation for studying differential equations. And now I want to define what a linear system of differential equations is, and then show you how to solve such systems given what we know. All right. So a linear system of first order differential equations has the form dx1 dt equals a11 x1 plus dot 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 plus a1n xn. So to be explicit, I'm going to put the time variable back in, just to emphasize that all the x's, all the variables here, depend on time. So for each variable, there's a differential equation of this form. Okay, and we assume that all the little a's are constants. So I'm being deliberately vague here because about the nature of the x's, because first order linear differential equations have applications in a variety of contexts, where the x's could represent positions, they could represent populations, they could represent sectors of an economy. So I'm just being deliberately vague and saying that our most general linear system of differential equations of first order has this form. Now the first order, that terminology simply means that only the first derivative appears in the equation. It's not the case that, for instance, the second derivative of a variable appears. So first order means just first derivative, and only the first derivative appears. Linear in the sense that if you cover up the left-hand side, what appears on the right is linear in all the x's. So a linear equation, very much like the ones we've been working with all semester. And so this is pretty much it. So this is a system of linear differential equations. Okay, so now this system will, yes, question?
So if the first derivative is, if it's linear, then the first derivative has to be constant, right? There shouldn't be no variables.
Well, the variable is time. So the x's don't have to be linear in time. The equations governing those x's have to be linear. So it's linear in the sense that I'm just taking a linear combination of all the x's.
Okay.
That's what we mean by linear. Any other questions? Okay. All right, so the future behavior, or the future behavior of the x's, and we usually put all the x's together into a single vector and call that x vector of time, or x vector is a function of time. So we put all of them together into a single column. Okay, so the future behavior of this column is determined by the system of equations so the system I had written over there, and the values of all of those variables at time t equals 0. So basically, it's not enough to just specify the system of equations that tells you how the x vector evolves in time. You also need to tell me what it was at some initial instant. So if you tell me what all the x variables had as values at time t equals 0 and the equation, then I can use that system to figure out what x of t will be at any time bigger than 0. So that's basically the idea. Any questions? Okay. So it's going to be very convenient for us to rewrite this system because it looks very much like the linear systems we've been working with all semester. It's going to be very convenient to rewrite that system as a matrix vector equation. So I'll define A to be the coefficient matrix, as usual. So notice that this is a square matrix. So this is an n by n matrix. All the little a's are constant. And so I can rewrite this equation in a simple way using vectors. So by the first derivative of vector x, what I mean is simply the column vector consisting of all the first derivatives. So I take the derivative with respect to time of each of the x's, put it into a column vector. And now by matrix multiplication, this is going to be equal to a times x of t. So automatically, using properties of matrix multiplication greatly simplifies the expression of this system of equations. Instead of writing out every equation in terms of all the variables, I can very succinctly write this as dx vector dt is equal to the coefficient matrix A times x. Okay. Any questions about that step?
Yes.
Okay.
Question, maybe not an actual question, but I don't get it.
So what
matrix.
what if I took out the t's and made all these b's on the left? Remember what we did there? So if I were to go back in time a few weeks and write the system a11 x1 plus dot 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 plus a1n xn equals b1.
Okay.
So if I wrote this system out, I don't think you would have any trouble with me writing it as ax equals b, right? So I'm basically doing the same thing, only now my b vector is the vector of all first derivatives. That's all I'm doing.
Okay.
Just so, like in this case, I can succinctly write that system as a single vector matrix equation. I can take this system of ODEs, differential equations, and write it as a single vector matrix equation. That's all I'm doing. All right. So now I'm going to show you in stages how we can solve this system if A is diagonalizable. Okay. So I'm going to begin in stages just so it's not overwhelming when we present the final result. So let's simplify the problem. Let's take a step back and look at this equation. All right, so we're taking a break from systems of differential equations, just taking a step back and going back to Math 3A. So y is a function of time. It's a real value function of time. A is a constant. So this equation tells me that the rate of change of y is proportional to y. But what's the only function up to a constant which has the derivative equal to a number times itself? Exponential, right? So y of t has to be equal to some constant, capital A. Well, let me not use capital A, because we're using that for the matrix. Y of t has to be that function, right? Because if I take the derivative of y with respect to time, the c0 gets brought right outside. And by the chain rule, the derivative of e to the at is c0a e to the at, which is a times y. All right? So using some 3A knowledge here. So the reason why I bring this up is because this equation looks a lot like that one, doesn't it? Right? So I need to remind you of how to solve very basic equations like this. All right? And really solving this is just remembering that y is proportional to the exponential function. Now I can express C0 in a useful way, right? Because if I plug in 0 for time, then that's going to be C0 e to the a times 0, which is C0 times 1, which is C0. So all in all, I find that y of t is y0 e to the at. So for this very, very basic equation, if you tell me what y is at time 0, if you tell me y 0, then I can tell you what y is for all future time. Right? Which is exactly what we're trying to do with our system of differential equations. Okay. Any questions about that? That's just 3A stuff. All right. Now let's take it one step further. So in this case, we have one function of time. Now let's increase the difficulty by saying that we have a system of functions which vary in time. Like so. Now this situation is really no different than this one, because in this situation I have dx1 dt is lambda 1 x1, so this equation just depends on x1 and x1 alone, as do all the other equations. They only depend on their respective variable. So using what I know based on that board, if I have a situation where my system looks like this, I can very easily write down the answer based on what we have over there. Right, so I'm basically just using that result n times. Okay. So each equation here is like a duplicate of the one on the right-hand side, just with different variable with a different constant.
Why are you multiplying by 0?
X1 at 0.
Ah.
These are functions of time, so you plug in 0 into the x.
So that's just a constant. Right?
Yep, all these are constants. The only variable is time here. Yeah. Okay. So now I can take all those numbers, all those functions, and put them together into a single vector. Right, like so. And now, if I now I can write this vector in terms of a matrix vector product. Okay, so hopefully it's not too hard to convince you that this, if you multiply these two matrices together, you get this column vector, because this is diagonal. So because you're multiplying on the left by a diagonal entry, each corresponding entry of this vector gets multiplied by the diagonal entry. All right. Everyone see that? Does anyone not see that? Okay. So basically what I'm trying to show you on this side of the board is the following fact. So dx1 dt equals lambda 1 x1 dot 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 dxn dt equals lambda n xn. That linear system, that very basic linear system, is the same thing as the x vector, dt, equals the matrix lambda 1 through lambda m on the diagonal times x. So I'm just rewriting that system of linear equations in terms of a matrix equation. And this has solution x of t is equal to e to the lambda 1 t, e to the lambda n t, 0, 0, times x0 vector. So I'm basically just expressing what we discovered in terms of matrices. So when our linear system has a diagonal coefficient matrix, the solution is simply the vector you get by multiplying x0 by e to the lambda t, e to the lambda n t.
Is that lambda n or lambda m?
That's supposed to be an n, sorry. I think my hand jittered just a little when I wrote that, yeah. Okay. So basically, if I start with a diagonal system, then I can write the solution in terms of a diagonal matrix times the initial vector. So we started with a single variable linear equation, showed that the solution had to be an exponential function. Then I generalized that to n copies of that equation, and then demonstrated that that linear system can be written as a diagonal matrix times x equals dx dt, which has a solution which can also be expressed as a diagonal matrix. And now, the part I need to convince you of, and I'm not sure if I have time for that, but we'll see. This matrix is in fact e to the d. If I define this to be e, actually let me define this to be a. I think that'll be better.
Number of entries. Is that what you mean?
I'm sorry?
Like number of entries?
Number of entries?
Like what is A represent?
A is the coefficient matrix.
Oh, okay.
So if I take the coefficient matrix, multiply it by time t, and then exponentiate, like we discussed when I first talked about diagonalization, you get the solution vector. Okay? So if it happens that our matrix is diagonal, then essentially what's happening here is that all the variables have decoupled. So the equations only depend on a single x variable. If this had involved x2, then we would say x1 and x2 are coupled together. Their equations are not expressible in terms of just x1 and x2 alone. But when our coefficient matrix is diagonal, all the equations decouple, and I can solve each equation in turn and express it in terms of a matrix.
So e to the CA is kind of scaling what the initial condition is at time equals 0, but A is itself an independent matrix that's plugged into that equation?
Yeah, so basically you take your matrix A, which is fixed, multiply every entry by t, then exponentiate that, using the definition we discussed on the very first day of diagonalization. Then you get a new matrix, you multiply that on the right by the initial vector, and that's x of t for all time.
That's your solution vector.
Yep. So now, to finish, and this is where I'll pick up after the exam review next time, this argument hinged on A being diagonal, but it turns out that this solution also works if A is diagonalizable. So if A is diagonalizable, then e to the t times A is defined by e to the TA. Remember I told you to star this equation when I went over this at the very beginning. So we have V times the diagonal matrix e to the t lambda 1, etc. So we can define the exponential of t times A this way. And the solution to dx dt equals A times x with initial vector x0 is e to the t times a times x0 when a is diagonalizable. Okay, so that's why we care about diagonalizable matrices. If our coefficient matrix happens to be diagonalizable, I can very quickly write down the solution to my linear system of differential equations. And I'm going to pick up with that next time. All right, so the progression was single variable equation dy dt equals a times y, had the solution y naught or y0 times e to the at. Then I moved up to a system of decoupled equations, showed that there's a parallel solution in terms of diagonal matrix. And now what I have to do next time is convince you that if A is diagonalizable, the same solution also works. E to the ta times x0 is a solution. All right. So then next time when we meet, I'll go over the practice exam, and then we'll continue with our discussions of differential equations. All right. Who has the signature sheet? Anyone have that? Yeah, please sign it before you leave, and I'll see you on Thursday. They're all in a box upstairs outside my office from 353. 353? Yeah.